Okay, thank you for keeping visiting this class. I'm happy to see you all here. Is it loud enough? I think, oh no, it was in a different class when I was trying to speak in the microphone and the person was saying, no, I do not hear what I tell. Good morning, how are you? So no lecture today. Today's lab, but not lab like wet chemistry lab. It's more computational lab. So we are in the first part of the PChem survey 700 something, 759, right? We do 2 months of quantum theory and 2 months with different instructor of statistical thermodynamics. And since it is very short time interval, we are trying to get only like some essentials. Quantum theory is not possible without calculus and differential equations, and you have some background, but to solve equations that have to be solved, 2 months are not sufficient. Therefore, we will do a little of computational thing with Matlab. So while I'm mumbling some introductory words, please open Matlab software on your laptops, and we'll continue going over basic skills, which we are going to complete in 3 Wednesday meetings. So one was last Wednesday, second is today, third one will be coming Wednesday. And on the following Monday, which I think it is February 7th, we will do presentations. So these subjects that we are discussing right now, it will be split between all class attendees by your free will votes. So like I'll do either Google Docs or just sign up sheet where you tell your preferences. And I'm just delaying it a little bit so you have more ideas what we are doing. But maybe on coming Monday, we'll do this democratic procedure. And then on the Sunday night of February 6th, I would gratefully accept emails with PowerPoint slides of your 5 minutes presentations, so that next morning we do not spend time on like putting memory stick into the computer or connecting, disconnecting. I'll just load them all and you'll just come make your talk, and so we'll count this as a midterm for this class. Huh? Whatever is Monday. What is our meetings are scheduled on Mondays and Wednesdays. February 7th. Okay. So, and then after you do presentations, we'll get codes that solve actual equations, and then you'll get another like round of getting acquainted and practicing those codes. And then last 2-3 weeks of the section, you'll apply these codes to the problems that we already agreed to study. Okay, so just basic plan. When we were here last Wednesday, I think we covered no, he doesn't want to copyright, or no. Okay, so I think we did complex numbers, definition of arguments and plotting, right? You remember it, and we also did derivatives and connection between sum and integration. I don't remember. Did we start any vectors, or I should start them right now? Oh, dot product. Okay. So scalar, which is dot product. And then we need direct product. Okay. So I'll try to cover about third today, and then we'll go further. I'll probably just use regular board. It will be better. Yes. But it's too long. It's not as it should be, right? No, I'll better just draw or use another another laptop. Okay, maybe it will be a little better. So, or finally, I'll find out. I'll draw things here. So, I remember we were speaking more about we were speaking about vectors in two-dimensional form. And to my memory, I was going around and making a little interview, right? And I think Hamid did recall for us an equation of scalar product as like length of vectors times cosine between them. Is that what we did last Wednesday? Okay. Now, next consideration of vectors is that if each vector is just two numbers, this dot product, scalar product is product of first projection plus product of second projection for each vector, right? You are fine with this. Now, let me ask if you feel comfortable with matrix multiplication. If what is the main rule of matrix multiplication?
If I feel comfortable with it.
Or if you remember something about matrix multiplication.
I did not do matrix multiplication since high school, so I do not remember.
Okay, that's okay. But what do you think? How one can multiply matrices?
I think like if we're talking about what's on the board, you'd have to do rows and then
Exactly. Thank you. And I think we do not need to do the rest of the interview. So everyone agrees, right? Row by column. So typically, we multiply square matrices. But even if they're not square, the same rule is applicable, right? So square matrices are good because by multiplying one square matrix times another square matrix, one get another third square matrix. But if the dimensions are incompatible, it's still possible. And here we can consider these two vectors that are on the board as two matrices. Just instead of 2 by 2, they are 2 by 1 and 1 by 2. And one still can practice the row by column rule, right? So we are taking row by column, which means A times C plus B times D, right? So let's, and if those were our two vectors, like if first vector has components A and B and second C and D, then this protocol of multiplying vectors as matrices will give the same result. So if this was like vector C1, and if this is a vector C2, then this was the just scalar product of vector C1 times C2. I'll make it substantial dot. Right. So let's do an example so that we can compare it with Matlab, like 1, 2, 3, 4. What will be the result? So 1 times 3 plus 2 times 4. 11, right? Okay. So what is interesting in this example? So we start with two vector objects which have direction, right? And we end up with a number, scalar, right? Let's just quickly check. So in your Matlab, try like C1 equals 1, 2, close bracket, C2 equals 3, next line 4, close bracket. And now typing C1 times C2. So I think Matlab is at least matching with our human understanding. So I'll quickly browse through, seeing that you didn't get any challenges from Matlab on typing it. Okay. Okay, so let me highlight an important thing. Yes, so if you look here, it is what all skills that we are doing right now are relatively doable. And for intellectual elite of a globe like graduate students, we can just, oh, okay, study it yourself, it's natural. But then there will be a lot of discomfort of these little things just because of syntaxes. So when we did an example on the like pen and paper, we used one matrix in the horizontal way, another is like row and column, right? So here we do the same. So for C1, we write them in one row. For C2, we do like first number, then we go to the next line, then the second number and close the bracket. And then they appear as a column. And then when we multiply C1 by C2, it is row by column, right? Okay, good. Okay. Rectangular bracket. Close. Oh, wait, it should, yeah, no. Open. Next line. Okay. 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 Excellent. Mhm. Okay, yeah, perfect, thank you. So now let's be a little bit crazy and do mathematical experiment. What if I just try different options and multiply same vectors in a different order? Like, what if I try to multiply C, D times A, B, where first one is column and second one is row. So of course you can very quickly do it, but what could be your opinions? What one may expect?
An error to occur?
Okay, error is one option. What else? So let me bring a context so that we think out of box. When we did row by column, we started with two vectors and we added and ended with a number. So dimensionality of the object was reduced from like linear set of numbers to just one number. If you swap the order, are we going to get the object of the same dimensionality? So just share your opinion, and you can either think and hypothesize or just immediately do it. But
I don't think it'll be the same.
okay, good enough. Thank you.
Yeah, I don't think.
Okay. Okay. I know that all knows the answer. So other dimensionality will be the same. Please teach us.
Dimensionality will be the same.
No. What will change with the dimensionality of the result of this operation? Is it same, increased, or decreased?
Increased.
Okay, so here's the voice of wisdom. Dimensionality is increased. Any opinions or thoughts?
No, I agree that I don't think you can do it because of the number of rows and columns, right?
Okay, so Arena expresses concern that for practicing row by column, the numbers of rows and columns must match each other, right?
I think so. Isn't there a rule where like the number of rows or columns in the first vector has to be the same as like the rows or columns in the second one?
Perfect, absolutely correct. I like it. Then I stop interviewing others. Sorry, I will interview you other time on other subjects. So, when we tell about size of matrices, what do we count first, row or column? Okay, let's start with rows and then columns. Okay. Now, how many rows and columns are for the first object? So rows equals 2, columns equals 1. Now, if you look on the second object, rows equals 1, columns equals 2. So Ariana told that number of columns in the first matrix should be the same as number of rows in the second. Do we have this match? We do. It's a little crazy. So the number of, it's just one row and one column, which it's not an actual matrix, but formally the numbers are the same. So we still can practice row by column procedure. And we can just go ahead. So if you take this element, if you go just this row and this column, we are getting the first element, C times A. And it belongs to, it would have index 1, 1, 1. Now, if you take second row in the first object, right, and multiply it by the first column in the second object, it should be just D times A, but by rules of matrix multiplication, it should be in a different cell of a matrix, right? So we'll put here D times A. Now, if we go to the first row of the first object and multiply it by the second column of the second object. So it will be just C times B, but it's different index, or it should be placed in a different cell. So C times B. And if we practice, I'm getting out of colors. If we go through second row of the first object, did I miss things? No, I think I'm doing right. Row by column will be D times B. So from multiplying two vectors, we are getting a matrix, right? So if dimensionality of a number is 0, dimensionality of vector is 1, just because one string of number, then matrix matrix has dimensionality 2. And depending on how we process vector multiplication, we can either decrease or increase dimensionality. When we do them row by column, we decrease, we get a number. When we do column by row, we get a matrix. And let's do a little example so we can compare our skills with what computer is doing. So let's do the same one. We had 1, 2, 3, 4. So row by column 3, row by column 6, row by column 4, row by column 8. Extra credit to anyone who finds mistakes, because I do them naturally. Okay, now let's go to Matlab. Recall we have C2 is a column, C1 is a row, and now do C2 times C1. 3, 6, 4, 8. 3, 6, 4, 8. Make sense? Okay, please just do it. I know it's a very simple exercise, but I want to make sure we all are on the same page. Excuse me. You do not need to redefine them. They are already defined. You can, yeah. By the way, Matlab is not a like person for chat partner, but sometimes it recognizes some of the human words. If you ask who, it gives a list of variables that are being defined actively. So let's type just C, hit enter. So that we, oh, okay. That's okay, that's no problem. Okay, yeah, thank you. Yeah, I see it. Yeah, thank you. Okay, thank you. Okay, thank you. Yes. Okay. Okay, thank you. So there are different ways to verbally address this situations, but the idea reducing and increasing dimensionality is quite needed. I'm going to jump forward without sufficient background, but it will be just as a little heads up. Very soon we will do eigenvalue problems. We already briefly chatted about it. So in narrow sense, quantum theory is just applied differential equations in the sense of solving eigenvalue problems. So anything that happens in the natural world, in many cases, can be reduced just to diagonalizing a matrix, finding eigenvalue of a matrix. So matrices or their corresponding differential operators are the heart of quantum theory. The vectors are analogs of wave functions, which we need to like define, make them philosophical interpretation. But like when we did a lecture, we had this wavy things, right? Wave functions, and they can be either as a continuous functions or as just set of numbers as vectors. So vectors and matrices or wave functions and operators are major players in this game, right? And if we have major players, just two kinds of major players, vectors and operators, which are represented by matrices and operators and wave functions on one hand, and matrices and vectors on the other hand. So what can we do with matrices and vectors? We can always multiply matrix by a vector, right? To get another matrix. We can add or subtract both vectors and matrices. And we can multiply vectors. And from this little example that we covered, we know that we can multiply vectors at least by two ways. From your general like math background, you know that there is also cross product, but it's only for three-dimensional. Here we have only scalar and dyadic. Sometimes people call it dyadic, but the idea is two types of making products of vector. One way of vector multiplication, which reduces dimensionality, which converts two vectors into a number. Another way of multiplying vectors, which convert two vectors into a matrix. So right now, I'm not going to give more details, but by creating a matrix out of vectors, it means that if we know vectors for some problem, eigenfunctions, we can construct an operator out of them. So there is a way, not only by acting by operators on a wave functions, but if you know some wave functions, they can serve to build a new operator. Do not try to, if you feel confused, don't worry, it's normal. The only thing that we can, there are two ways of multiplying vectors, and it is really important. So another little piece of information. When we met last time on Wednesday, I was trying my best to pursue the analogy between functions and vectors, and to introduce scalar product of functions, right? So depending on specifics of quantum problem, one is using either continuous functions or vectors. And it is a little discomfort because they both, matrices and vectors, are tools, but the natural objects are independent of the tools. They objectively exist. And there is a way to unify both vectors and functions into one abstract mathematical object. So I'm going to briefly introduce it, and later on we will practically get to it. So the thing that I'm going to tell is Drack notation, and for column vector, or regular function, he suggests a notation of such angular bracket, and one typically writes like wave functions there. So this can be either, this can mean either a vector or a wave function that depends continuously on a variable. So column vector. There is different notation where the bracket goes to other side. Then it corresponds to a row vector or to conjugated wave function. So with this notation, one can practice the same things as we did in our little example. So if one multiplies these objects in a way that brackets look outwards, then it will correspond to row by column and will give a number. If you multiply them opposite, so that angles look inside, it will be column by row, and it will give a matrix or an operator. The name of the there are specific names of this notation of this bracket. So it uses angular brackets, right? And when we put brackets together, we get a number. So when uses the word bracket, and since we always look to obtain a number, which is like result of measurement, right? we need to merge these two vectors together. So one calls the one that looks arrow to the right cat and one that looks arrow left bra. And then bra and cat must be placed together to form a word bracket. And it is most natural. If we do this column by row, then it is cat times bra. Okay. Let me check. I do have the list of subjects on the other equipment. So we did scalar and direct product and Dirac notation, right? So our next thing is actual matrices, transpose, determinant, multiplication, inverse matrix. And I really want to cover eigenvalue today, which is the hardest and most important. What did I type? Okay, so going to matrices. Transpose, determinant, matrix multiplication. I know what I want to say, but it's too much. I just don't have enough letters in the alphabet. So generally, if we are speaking about a matrix, we will need to recognize that they eventually can be complex. Complex, not that they're so complicated, but complex numbers, right? With real and imaginary parts. And we will need operations of dealing with matrices, which we can like add, subtract, multiply, inverse, find eigenvalues. So one of the procedures for matrices is so-called transposing. So what if we just manipulate vectors and matrices, and by some reason we need row instead of column vector? We just quickly need to convert bra into cat. So without thinking what does it mean and why we need, but when we manipulate with matrices in the software, we need this operation. And transposing means making a mirror reflection of a matrix along its main diagonal, right? So if it was a square matrix, it just swaps off diagonal parts, diagonal stays the same. If it was a vector, then it converts row into column or column into row. So and in addition, there is one typically uses a little dagger or plus or cross symbol, which means Hermitian conjugated transpose, which simultaneously swaps the off diagonal elements. So put this one here and this one there. And in addition, the transposing operator swaps the sign in front of each imaginary component. So if we do this transposing, we will get A minus I B, C minus I D. What? Yeah, E minus I F and G minus I H. So in Matlab, this procedure is done just by apostrophe sign. So let's go to Matlab and do some experiments. I'm lazy to type a big matrix with all of things complex. Let's do, just look, our C1 is row. If you type C1 apostrophe, it becomes column. Our C2 is column. If you type C2 apostrophe, it is row. If we multiply C1 times C2, it is a number. If you multiply C1 apostrophe, C2 apostrophe, it is a matrix. So this apostrophe symbol makes inversion in respect to a diagonal. And if we define a matrix or a vector with if you define like complex vector and we do this transposing, so this apostrophe flips it, it converts column into row, and it flips signs in front of imaginary component. Okay, anyone has a challenge in typing this, or everyone is fine? Please try. Yeah. Okay. So there is another thing that goes against this matrix logics, but in addition to little apostrophe symbols, there is a dot symbol that I think we practiced last time. So if you want to cancel any rules of matrix multiplication, then we use this little period. Doing once again, C1 times C2 will be like 11, but if I put a little period here, then it, so if I use vectors of the same number of rows, numbers of columns, and use period between in the, together with multiplication, it doesn't change dimensionality. It just multiplies them element by element. Okay, and I'm not making a circle because it's less important. When something is truly important, I'll make another circle over or rows, make sure that everyone gets it for sure. So yes, there were a question. Period. C1 period multiply C2 apostrophe. I'm going to write something and then ask what do you think about it? Okay, so I'm going to walk around and make a little interview. What do you think of this writing? And again, don't hesitate. Just share what you think.
That looks terrifying.
Okay, for me too. But how do you characterize or like if you do not have screen and we need to communicate content of this board to someone who's on a phone line? We're not going to say it by number like A11. Just briefly try to summarize which objects and what do you think of them?
We're multiplying two matrices and we know the numbers for the first one, but not the second one. And we know the result.
Okay, yeah, good. Thank you. So let's keep.
Here we have one matrix with known numbers, another one with unknown numbers.
Anything else? Hua?
Multiplying a known matrix by a function which we do not know, and we get a result that we know. It looks like an eigenvalue thing.
Not quite eigenvalue, but it is a problem that has some unknown that needs to be solved, right?
Yeah.
Okay. Ariana?
It looks like we have a resultant vector and an unknown vector multiplied by a known matrix, and we have to figure out what the unknown is.
Okay, yeah, all correct. I like it.
Can I ask something? Do the known vectors are same or different?
No, it's just different numbers. So no, all elements in matrix are known, all elements in C are known, but x1 and x2 are unknown.
Okay, so then we have a known matrix that we will multiply with an unknown matrix that will give us another known matrix. That's what I can see.
Okay, yeah, good, thank you. Okay, you can answer your first impression. What do you see on the board?
Let's see, is there an inverse of a matrix?
Okay, good. that was quick. You definitely took some linear algebra. Okay.
I see what everyone else has been seeing. You know, we have a we have a matrices that we know, and then we have outputs that we know, but we don't know like what's happening, what we're multiplying by, to get our known outputs.
Yeah, thank you. Haley, I have no doubts that you will answer something smart and reasonable, even if you do not see the whole picture.
Thanks. It looks like you're multiplying a known matrix times an unknown column vector to get a known column vector. And if you have applied like linear algebra, maybe you could solve for the unknown vector.
Yep, absolutely correct. There is a question that I should be able to answer, but I do not have idea right now. In which life situations such equations need to be solved? Did you ever saw such equation in your like mid school, high school?
Yes.
So what is a practical example in for either like trains arriving to the same station or people measuring like apples and oranges? Can you design an example that will be practiced through this equation? Maybe let's think about it and as a little addition to homework, and then you tell next time, because I need such example for next year class.
You know the speed and you know the number of miles, but you need to find the number of hours.
Okay, but it is what you're telling will be just velocity times number of hours will give you distance that you travel through, right? But here it is not just, it will be like problem with two numbers known and one is unknown. And here we do have two unknown numbers and they're connected. I'm just a blank on giving examples, which I should give in the ideal lecture. But this is, one can call it linear algebraic equation when by combining. So if we open this equation by multiplying matrix by vectors, it will be like a11 x1 plus a12 x2 equals c1 a21 x1 plus a22 x2 equals c2. So those are it. This matrix equation corresponds to a system of linear algebraic equations where one knows all coefficients and one doesn't know the unknown variables x1 and x2, right? These equations were used a long time ago. I think you may find for your education component who was using this equation, and it goes much before differential calculus. Yeah, Kramer, there is also a Gauss way to solve this, but I'm blanking on examples of practical problems that needed. There, if we have 2 by 2 or 3 by 3, one can do it by pen and paper. There are ways of balancing, like multiplying each term in one equation by a factor, then adding and subtracting, and then solving for x1 and x2, right? I think we all had it in like middle school or high school algebra, more or less, right? But if we have simultaneous work with multiple independent unknown variables, one needs an algorithm that helps to solve it as quick as possible. And especially if you have computers, we need something universal, that we do not program individual steps, but do some common routine to solve equations like this. I think one of examples is making a schedule for like buses, but I would be happy to give more details. So if anyone comes with an idea, maybe next Wednesday or Wednesday is better. Mondays are busy. Just come up.
This one here I used to use with students, but like dimes and quarters, like this, these are just examples, but if you have a collection of dimes and quarters that are worth $15.25, and you have 103 coins in all, how many of each do you have? So then you set up the equation.
Okay, yeah, thank you. So there are universal ways to solve this type of equation and a universal way to program it into a computer and a language to accommodate this way to solve this linear algebraic equation. So one typically calls the like the matrix as a big number vector. Sometimes one writes as a vector and another vector also as a vector. And this equation can be summarized as matrix multiplied by a vector gives another vector. Or matrix and vector unknown and the vector x is unknown. So basically, on which vector our matrix must act to fabricate predominantly known vector C, right? And there is an abstract way to solve this equation. If we assume that there is a way to divide matrices, then it will be applicable here. Like if you have function x, just regular, and then function 1 over x, their multiplication will give 1, right? And we can also write it down as x times x to the power minus 1 will be 1. So what if we do a little mathematical experiment and hypothesize that there is a such matrix which we will label like inverse matrix by multiplying on regular matrix, it will give unitary matrix with all diagonals in the center, all ones in the center and zeros otherwise. So first we assume that there is such an inverse matrix that will give this ones inverse. If this assumption makes sense and if no one objects, we can use it towards our equation. We will multiply left and right part by this inverse matrix. Then it will be a minus 1 times a times x equals a minus 1 times c. And if we agree on this property, abstract property, that a times a minus 1 will be 1, will be like matrix with only ones on the diagonal. And we know that matrix with ones on the diagonal multiplying on each vector will just reproduce the vector itself. Right? So if you believe this little trick, then we can erase these matrices and get a solution. So our unknown vector x will be inverted matrix multiplied by multiplied by the known vector c. So inverted matrix times c will get x, right? I'm not sure that we will practically need this equation for quantum course, but in the like sequence of linear algebra steps, it is needed just to have a consistent view, and we needed to get to the next stage of eigenvalues, which will be truly needed. Okay, so let's make an example. So like a equals 1, 2, 3, over. We have a matrix. We can define C as like 5 and 6. And now we want to find such a vector X which will match our matrix equation. So there is a command inv for inverse. So right now I'm skipping the algebraic procedure what is inverse matrix, although it is not as difficult. And some of you I'm sure know about it. So if we practice this inversion operation, it generates a matrix of the same dimension with but different values. So if I multiply this inverted matrix by the original matrix, it does generate a matrix with only ones on the main diagonal and zeros elsewhere. And we can prove it by pen and paper, but it will just take time. And now, if I apply this inverted matrix to the C, you'll get some numbers which I can call as X. And so basically linear algebraic problem, this training linear algebraic problem is solved. And now we need to check whether we got a right solution. If we did everything correctly, then original matrix A times our newly found vector C must be equal to the vector X must be equal to the vector C. C was 5, 6, and A times X is also 5, 6, right? So we get correct answer. So please, I know that not everything is visible, but try to reproduce. Let me know if some part of this exercise needs to be displayed. A, C, and inverse. And then, yeah, this is main thing. I'm going to browse through sheets and check if you feel comfortable with this little exercise. Enter. Okay. And now X equals inverted A. Yeah, times C. And now try A times X. Does it look similar to C? Type just C upper. Are they the same? So you solved the equation right? Yeah, good. But why your C is matrix?
I just made this one here, but I did it before earlier.
Okay.
But your C value there, did it have any relationship with A, or was it random numbers? You used the C.
I did random numbers.
So I just used random numbers to define my A, inverse of A, and then I multiply by C.
Okay.
Thank you.
Yeah, thank you. Okay, and yeah, good, thank you. Okay, good, thank you. Yeah, it's good. Yes, great. Okay. I already saw. So, yeah, excellent. Thank you. Okay. So we still have some like 10 minutes. Let me double check my cheat sheet where we are and what else we need to do. So, oh, we didn't do determinant. Matrix multiplication is quite natural. We even we did it before. We did inverse matrix. So we need to briefly speak about determinant and then start eigenvalue problem. So what is determinant? Why do we need it? Okay, probably then we need to speak if there is not enough enthusiasm. So when mathematicians of the it was practiced by about the time of Galileo, and when there was algebra, but there were no calculus. And when practical problems were important to solve, and there were no computers, a mathematician needs to count his or her efforts before starting solving, because it can be time demanding. And before solving the linear algebraic problem, ancient mathematician needs to decide whether this problem is solvable. And again, we are not mathematicians and it's not a mathematical course, but there are circumstances when equations like this do not have solution or give something unreasonable. Especially if one, or just it's not a well-formulated problem. For example, if one repeats one equation twice and just writes it down as a matrix equation, it's just a nonsense. It will be two values will repeat each other, and there is nothing wrong. It just no sense to do it. It's not solvable and shouldn't be solved as a matrix equation. And in such situations, when elements of matrix are not unique, when they just repeat each other, like if there are like 1, 2, 1, 2, so it's a bad matrix. Well, not bad. It's not applicable for this problem. So there is a criterion to say whether it is good matrix or bad matrix. And this criterion is referred to by a word determinant. So by telling if determinant is non-zero or zero, one can tell whether it's worth of spending effort to solve linear algebraic equation. So it's one use of the word determinant. And the practical rule would be for this A11, A12, A21, A22. So the practical rule for this determinant will be product of those on the main diagonal minus product of those away from the diagonal. So if our matrix was 1, 2, 3, 4, then the determinant will be 1 times 4 minus 2 times 3, which will be 4 minus 6, answer minus 2, right? So when we did it in the Matlab, it gave this minus 2. there is, so this concept of determinant is a bridge from medieval algebra to modern linear algebra, to the chapters of algebra that are needed for quantum theory. So when we solve in the very near future, maybe not today, but it's an important, when we solve eigenvalue problems, one technically needs to find determinants of a special matrices, and it is critically important. And here, does anyone needs to live literally at 12:30? Just raise hands. I will accommodate. Then I'll use few minutes more just to complete the thought. So if we so I'm skipping an introduction, go to practical side. If we need to find eigenvalues of this matrix, I'm just reproducing same notation, 1, 1, a 1, 2. I probably may have just copy pasted to 1, a 2, 2. So the practical way is to subtract a number, the same number from each element on the diagonal, find a determinant, and make it equal to 0. So when one practices this prescription, then one is getting the following equation: a 1, 1 minus lambda times a 2, 2 minus lambda minus a 2, 1 times a 1, 2 equals 0. So in this equation, we assume that all elements A are known and lambda is not known. And if we decide to open brackets, we'll get lambda squared minus lambda times a 2, 2 plus a 1, 1 plus a 2, 2 a 1, 1 minus a 2, 1 times a 1, 2 equals 0. So I really want to hear your impressions. So this is an equation where lambda is unknown. So what do you think by looking onto this equation?
I believe so, but
How do you characterize? Or if you do it again, if you need to describe it by a formula without showing the equation, what is looks like?
you would solve for the unknown to solve for lambda.
Yes, but how? Is there a specific terminology for this type of equations? Is lambda in which power?
It's in the second power, so
Yes, and second power is sometimes called
quadratic.
yes. So it's quadratic.
Quadratic.
Okay, yeah, thank you. Any other comments?
Probably use the quadratic formula.
Okay, yes. So it can be solved, right? We all know how to solve it.
What's the question?
How to solve this equation
Is Matlab?
without Matlab?
Huh?
How to solve this equation without Matlab?
I don't know.
Come on. Let me give another example, like x squared plus x plus 1 equals 0. So how to find x? How to find x?
Okay, we need to find x2 first. No.
Just look into Wikipedia for quadratic equation, right? Yes, just do it right now. You'll find it fun. Lola, any comments on how to solve or how to characterize what is this equation?
It's a quadratic equation.
And if matrix will be not 2 by 2 by like 100 by 100.
I don't understand, sorry.
Like what is a common name for functions which use like different powers, like first, second, third, fourth?
Polynomial.
Yes. Okay, so it is a polynomial equation. Yeah, thank you.
No, just that it's a quadratic equation and you could solve it either with the quadratic formula or factoring, though in this case, probably the quadratic formula.
Okay, yeah, thank you, Ryan. Hamid?
We can use this one.
Exactly. So Hamid is reproducing the equation with discriminant.
Yeah, just use the quadratic formula.
And if it is third power or fourth power?
Then how do you solve a polynomial?
Okay, yes, yeah, absolutely correct. Haley, any words of wisdom?
No.
Any general words like what do you do when you need to solve polynomial equations of higher order?
I don't remember.
Oh, I decline to solve them. Okay, so because we need to depart several minutes ago, I'm just completing the thought, and we are a little bit behind of my own schedule, but I'll try to just concentrate next Wednesday. But I will give more background and introduction for eigenvalue problems, and we went only through the just heart, the essence. When one needs to find so-called eigenvalues of a matrix, one forms characteristic equation in matrix form. And then through taking determinant, we convert matrix equation into polynomial algebraic equation, which we were trained to solve again in mid school and high school, right? For like second and third power, and sometimes fourth. And if it is high power, humans are not as efficient. But generally, it is very standard equation, and general way is to plot this function and look where it intersects the x-axis. And where it intersects the x-axis will be the answers, several answers for this lambda. So these lambdas will be eigenvalues of that matrix. But to go from this matrix equation to algebraic equation, we need to practice determinant. Okay, I think it is enough because you may have scheduled activity, but I don't remember if you have any homework. Probably not. Just relax, accumulate energy. And see you on Monday, where we will do continuation of lectures on from content factors, and on Wednesday we will complete this Matlab stuff. Okay, thank you. Yeah.